Welcome to GE Fun Facts Online. Today, we are abandoning the Badlands for the server room, because the biggest excavation in history is currently happening inside a computer. For over a century, the field of paleontology has been romantically defined by a singular image, the dusty explorer. You know the archetype. A sun-beaten scientist, standing in the Morrison Formation or the Gobi Desert, wielding a rock hammer and a delicate brush, painstakingly revealing the white glint of bone from red sandstone. It is a discipline grounded in the tangible, in the physical weight of rock and the tactile geometry of fossilized remains. But we are witnessing a seismic shift. In 2026, the frontier of paleontology is no longer just about digging into the earth. It is about digging into code. We are entering the age of digital paleontology, where artificial intelligence is cracking codes that have stumped humans for over 100 years. The catalyst for this revolution is a new AI application, colloquially dubbed DinoTracker by the press. Developed by a collaboration between physicists at Helmholtz Zentrum Berlin and paleontologists at the University of Edinburgh, this tool has done something previously thought impossible. It has taught itself to read the chaotic, eroded, and ambiguous language of dinosaur footprints without human instruction. And the results are staggering. This AI has not only solved local mysteries on the Isle of Skye, but has potentially rewritten the timeline of avian evolution, finding bird footprints tens of millions of years before the first known bird, Archaeopteryx, ever spread its wings. Today we are going to break down exactly how this technology works, why it is superior to human eyes, and what it tells us about the ancient world. To understand the magnitude of this AI breakthrough, we first have to understand the unique frustration of studying dinosaur footprints, a field known as paleoichnology. Steve Broussat, a renowned paleontologist at the University of Edinburgh, describes the discipline's central challenge as the Cinderella problem. It is a brilliant analogy. When a paleontologist finds a footprint, they are essentially holding a glass slipper. They know someone was at the ball, and they know roughly how big their feet were. But the princess, the dinosaur itself, is long gone. Unlike bones, which are direct parts of the animal, footprints are records of an interaction between biology and geology. A footprint's shape is determined not just by the anatomy of the foot, but by the consistency of the mud, the speed of the animal, the slope of the ground, and millions of years of subsequent erosion. A Tyrannosaurus rex walking through stiff clay leaves a very different print than the same T-Rex running through soupy riverbed mud. For over a century, human experts have tried to classify these tracks by eye. They look for specific features: the angle between the toes, the sharpness of the claw marks, the presence of a heel pad. But this method is fraught with subjective bias. If a researcher expects to find a certain dinosaur in a rock formation, they are subconsciously more likely to interpret a vague three-toed blob as belonging to that dinosaur. Worse, the taxonomy of footprints is a mess of synonyms and disputed categories, with different experts using different names for the same shapes. This is where the DinoTracker project began. Gregor Hartmann, a physicist at Helmholtz Zentrum Berlin, realized that the problem wasn't a lack of data, but a lack of objective interpretation. The human brain is excellent at pattern recognition, but it is also an engine of bias. We see faces in clouds and familiar dinosaurs in amorphous holes in the ground. Hartmann proposed a radical solution: remove the human from the loop entirely. Now this is where the computer science gets interesting. Most AI applications in science use what is called supervised learning. In this approach, you feed a computer thousands of images labeled by humans. You say, this is a cat, this is a dog, over and over until the computer learns to distinguish them. But if you used this method for dinosaur tracks, you would simply teach the AI to replicate the biases and errors of human paleontologists. If the experts were wrong about a footprint classification, the AI would learn to be wrong too. Hartmann and Broussat chose a different path: unsupervised learning. They utilized a sophisticated neural network architecture known as a disentangled variational autoencoder, or VAE. To put it simply, you can think of a VAE as a hyper-efficient compression algorithm with an imagination. The researchers fed the system nearly 2,000 silhouettes of fossilized footprints from the Triassic, Jurassic, and Cretaceous periods, along with modern bird tracks. They didn't tell the computer what the tracks were. They simply said, look at these shapes, find the simplest way to describe them mathematically. The AI broke the images down, compressing them into a latent space, essentially a multidimensional map of shapes. To do this effectively, the AI had to figure out which features of the footprints mattered most. It ignored the noise, like cracks in the rock or random erosion, and focused on the signal. Remarkably, the AI independently discovered 8 key features that define the variation in dinosaur feet. It didn't know the words for toe spread or heel impression, but it mathematically isolated these concepts. It identified variables like digit spread, which is the angle between the outer toes. It looked at heel position, weight distribution, and something called heel loading, which is the specific pressure depth of the heel. It even detected left-right asymmetry, the subtle differences in how the foot rolls during a step. By plotting every footprint against these 8 variables, the AI created a morphospace, a 3D galaxy of dots, where every star was a footprint. Tracks that were similar clustered together, forming natural families. When the researchers finally overlaid the human-created labels onto this AI-generated map, the results were vindicating. The AI's clusters matched expert consensus about 90% of the time, but it was in the 10% of disagreement that the groundbreaking discoveries lay. The most shocking finding from the AI analysis came from a set of tracks dating back to the late Triassic and early Jurassic periods, over 200 million years ago. For decades, paleontologists have been puzzled by certain small, 3-toed footprints from this era. They look uncannily like bird tracks. However, the fossil record tells us that birds didn't evolve until much later, in the late Jurassic, around 150 million years ago, with creatures like Archaeopteryx. The consensus was that these Triassic tracks must have been made by some other reptile that just happened to have bird-like feet, a case of convergent evolution. The AI disagreed. In the AI's impartial morphospace, these ancient footprints didn't just look kind of like bird tracks. They clustered deeply and undeniably within the bird group. The mathematical signature of their weight distribution, toe splay, and heel structure was indistinguishable from modern avian footprints. This leaves paleontologists with 2 tantalizing possibilities, both of which rewrite the textbooks. The first is the early bird theory. This suggests that birds, or their direct ancestors, evolved tens of millions of years earlier than we thought. They were hopping around the feet of early giant dinosaurs in the Triassic. But their hollow, fragile bones have simply never preserved as fossils. Only their footprints remain as ghost evidence. The second possibility is the perfect mimic theory. This implies that a group of non-avian dinosaurs, likely early theropods, evolved feet that were functionally identical to birds. This would mean that the biomechanics of walking like a bird were perfected by evolution long before flight was ever invented. As Broussard noted, the AI is forcing us to confront the data without our preconceptions. It doesn't care that Archaeopteryx is supposed to be the first bird. It just sees the geometry, and the geometry says, bird. Closer to home, the AI was deployed to solve a mystery on the Dino coast of the Isle of Skye in Scotland. This windswept island is one of the few places in the world preserving the Middle Jurassic, a time gap in the fossil record often called the Dark Ages of dinosaur evolution. Researchers had found hundreds of tracks on the tidal platforms of Skye, but they were messy. The constant battering of the North Atlantic waves had eroded them, and the dinosaurs had originally walked through sticky lagoon mud, distorting their prints. Experts argued for years, were these the tracks of early meat-eaters, the theropods, or early duck-billed herbivores, the ornithopods? The distinction is crucial. If they were ornithopods, it would mean these plant-eaters had exploded in diversity millions of years earlier than believed. If they were theropods, it changed the predator-prey ratios of the ecosystem. The AI analyzed the chaotic Skye tracks and cut through the noise of the erosion. It identified the deep signal of the weight distribution, specifically the heel loading variable. It concluded that the tracks were undeniably made by ornithopods. This digital confirmation provided the first solid evidence that these herbivores were thriving and growing to large sizes in the Middle Jurassic lagoons of Scotland, fundamentally changing our understanding of that ecosystem. One of the most exciting aspects of the DinoTracker project is that it isn't locked away in an ivory tower. The team has released the tool as a smartphone app. This represents a massive democratization of paleontology. Previously, if a hiker or amateur fossil hunter found a weird depression in a rock, they had to take a photo, email a local museum, and hope a busy curator had time to look at it. Often, these finds were ignored or misidentified. Now a user can snap a photo of a track with their phone. The app uses photogrammetry principles to analyze the depth and shadow, processes the shape through the neural network, and returns a probability score. For example, it might say 85% likelihood of theropod, closely resembling grallator. This turns every hiker into a potential research assistant. We are approaching a future of citizen science 2.0, where the sheer volume of data collected by the public feeds back into the scientific models, making the AI smarter. This mirrors other successful initiatives like Fossil Finder or the DigiVolume project, but adds an analytic AI layer that is truly unprecedented. While the AI app is the headline grabber, it is supported by a suite of other digital technologies that are replacing the plaster jackets and dental picks of the past. We are seeing the rise of photogrammetry as the people's 3D scanner. This technique was instrumental in the recent excavations of the Dinosaur Highway in Oxfordshire. Researchers uncovered one of the longest dinosaur trackways in Europe, a 220-meter path walked by a herd of sauropods 166 million years ago. Because the site is an active quarry, the tracks couldn't be physically preserved. The rock would eventually be crushed for construction. In the old days, this data would be lost. Instead, The team used drone-based photogrammetry to create a millimeter-perfect 3D digital replica of the entire site. This digital twin allows researchers to study the tracks forever, manipulating lighting to see shallow impressions invisible to the naked eye. Then there is Lidar, or light detection and ranging, used for mapping megasites. At the Costa dell'Anglone track site in Italy, hundreds of footprints are scattered across a vertical rock face. Hanging off a cliff to measure tracks is dangerous and inaccurate. So researchers used ground-based Lidar to scan the entire cliff, shooting millions of pulses of light to create a point cloud. Algorithms then stripped away vegetation and weathering, revealing the tracks with clarity that human eyes simply cannot achieve. And perhaps the most sci-fi advancement is the use of high-energy CT scans to look inside fossils. In the past, preparing a delicate fossil skull meant risking destroying it. Today, AI models are automatically segmenting bone from rock in CT scans. A recent study on Protoceratops embryos used this to separate tiny, fragile bones from the egg content, allowing us to see things like the inner ear canals to determine the animal's sense of balance. The digital revolution isn't just about shape, it's about substance. For a long time, it was dogma that soft tissues like skin and proteins decayed within weeks of death. That dogma was shattered by Mary Schweitzer, and now, AI and advanced imaging are taking this molecular paleontology to a new level. Researchers are using synchrotron rapid scanning X-ray fluorescence to map the chemical ghosts of soft tissue. We can now detect the chemical signature of melanin pigments. We know that Microraptor was iridescent black, and Sinosauropteryx had a ginger and white striped tail. AI models are even being trained to recognize the microscopic texture of fossilized skin in CT scans, recently hinting at the presence of a dewlap, a flap of skin, on Edmontosaurus specimens. All of this leads us to a philosophical shift. If we can 3D scan a site like the Dinosaur Highway and then let the quarry destroy it, have we really preserved it? Most paleontologists argue yes. A physical trackway erodes every year it is exposed to the elements. A digital file is immutable. Furthermore, a physical site can only be visited by a few. A digital site can be studied by a student in Mumbai, a professor in Berlin, and an enthusiast in Buenos Aires simultaneously. This is the ultimate promise of the AI revolution in paleontology. It is breaking down the barriers of access. It is stripping away the subjective biases of the lone genius expert. It is revealing that the rock record is far richer, denser, and more surprising than we ever dared to dream. The dinosaurs may be gone, but thanks to the marriage of silicon and stone, their digital ghosts are more alive than ever. We are no longer just looking at their footprints. For the first time, we are walking alongside them. Thanks for listening to G Fun Facts Online.